Hi everyone, welcome back. So before we get into the next set of scenarios under which we can do resonance or we can construct resonance forms, we're going to talk about some terminology. And this is terminology that's going to be useful even in later chapters. Okay, so when we go to chapter 8, chapter 10, this terminology is still going to be handy. Okay, so let's talk about this. And what we're going to do here is we're going to define, or in some sense define, or instead of defining, I think what we're going to do here is differentiate vinylic and allelic positions. Okay, so two terms, vinylic and allelic positions. So we're going to differentiate between the two, understand what are these and how is one different from the other. So these both they both relate to double bonds. Okay, so when we have atoms that are double bonded to each other, so let's say when we have two carbons, we don't need double bond. Sorry, we don't need the carbon. So let's say if we have a double bond between two carbon atoms, okay, and I'm just randomly, I've just drawn like a structure. Okay, it's a very random structure that I've drawn there. There. Okay, so now we have a very random structure that I've drawn here, and just to make sure that we're able to understand what vinylic and allelic positions are, or vinylic and allelic positions, or if we are specifically talking about carbons, we can call them vinylic carbons and allelic carbons. So vinylic positions, these refer to, or the vinylic carbons are the carbons that are engaged or that are part of the double bond. So the two carbons here which have a double bond between them, okay, the ones that have a double bond between them, these are called vinylic carbons. Okay, or if it's not a carbon, we can just call it a vinylic position. Okay, so the atoms that are part of the double bond, okay, that have the double bond between them, those are vinylic. And any position or any carbon that's connected to that vinylic carbon is called an allelic position or an allelic carbon. So for example, this carbon here, it is connected to the vinylic carbon. So is this carbon. So these carbons, they are both called allelic carbons or allelic positions in general. Similarly, on the other side, if you look at it, okay, we have an oxygen. We have that oxygen which is connected directly to the vinylic carbon, and we have a nitrogen that's connected directly to the vinylic carbon. So these are both allelic. So these are the allelic positions. Okay, so atoms that are part or that have the double bond between them, a pi bond between them, they are vinylic. And positions or atoms that are connected to vinylic positions, they are allelic. So that's an allelic position. Okay, so we need this for the next set of scenarios that we're going to see. Okay, the difference, or we need to understand the difference between what a vinylic and an allelic position is. In fact, we're going to be talking about allelic position, so we just need to understand what is an allelic position. Okay, so the next scenario that we're going to see where resonance is possible is when you have a carbon when you have a positive charge on an or at when you have a positive charge at an allelic position. Okay, so we have a positive charge at an allelic position. So this is the next scenario where we can do resonance. Now this positive charge, okay, in most of the organic compounds that we're going to see is on carbon. Okay, but it could be on other atoms as well. Realize that. Okay, maybe instead on is on carbon, I should write could be on carbon. Okay, so the positive charge could be on carbon. So let me show you an example of this. So we have a positive charge in this structure, and if you look at the positive charge, it is at an allelic position. So I'll let you think about it a little bit while I draw now the structure. Okay. Let's say there. Okay, so those are two structures that we're going to use for this demonstration here. In fact, I'm going to rewrite this structure because I did draw it really big. You have that. Okay, so let's say you guys have some time to think about it. So is this positive charge on an allelic position? Okay, so if you look at the positive charge, it is on a carbon that's connected to a vinylic carbon, or it is directly connected to a double bond. So this positive charge is vinylic. Okay, this is vinylic. In fact, we can call it a vinyl cation. Okay, vinyl cation, because it's a cation at a vinylic position. So we can call it a vinyl cation. So whenever we have a scenario where you have a positive charge on allelic position, we can do resonance there. So what we can do is we can take this pi bond, okay, and move it to the space between the vinylic carbon and the allelic carbon, which bears the positive charge. Okay, so we take the pi bond and move it to the space between the vinylic carbon and the allelic carbon that bears this positive charge. And this is going to bring us to the next structure. And I think for simplicity, okay, just as a help, I'm going to actually number these carbon atoms. So 1, 2, 3, 4, and 5. And you don't have to do this. I'm just doing it so that we can see, you know, how things are moving, where the bond's going. So if you notice, the pi bond or the double bond which was between carbons 2 and 3, and now we've moved it to the space between carbons 1 and 2. And again, I want to pay attention to the arrow itself. These arrows are very important. Starts from the pi bond, goes to the space between 1 and 2. So my next structure is now going to have a double bond between 1 and 2. 2 and 3 should have a single bond between them. 3 and 4 had a single bond between them, and then 4 and 5 have a double bond. Okay, so we have 1 here, 2, 3, 4, and 5. So that's the scenario that we have right now. So the double bond moved over to the space between 1 and 2. single bond between 2 and 3, single bond between 3 and 4, which was already here, and then a double bond between 4 and 5. Okay, so now at this point, this structure is not complete because we haven't included any formal charges yet. And there is a formal charge, a positive charge on that third carbon atom, carbon number 3. Now, why would that be? Because if you think about this pi bond, this was 2 electrons shared between carbons 2 and carbon 3. So carbon 2 contributed 1 electron, carbon 3 contributed the other electron. We took both electrons and moved to the space between 1 and 2, so that now there's a double bond between 1 and 2. So carbon 2, it still gets to keep its 1 electron, but the electron that carbon 3 had contributed, that's gone. Okay, so that's why it has a positive charge. If this doesn't make sense, just go ahead, do the formal charge calculation, and you should see that there will be a positive charge on carbon number 3, and that's the only carbon which would have a positive charge on it. Okay, so we've got resonance forms. Now, is this carbocation allelic at this point? Okay, is this positive charge? Carbocation is the term used for carbons that bear positive charges. Okay, so is this positive charge allelic at this point? And the answer is yes. If you look at it, this carbon here, carbon number 3, it is connected to carbon number 2, which is involved in a double bond. It is also connected to carbon number 4, which is involved in a double bond. So now we just came from this side, you know, we are moving from basically from left to right. So what we'll do is we'll keep moving forward. If you go back, you could try drawing it. It is going to bring you to the same structure, you know. So if I say that, okay, this is an allylic positive charge, and so what I'm going to do is I'm going to take this pi bond and move it to the space between 2 and 3. And if you draw the resulting structure, you will come back to the same structure. Okay, so try that for sure. So we're not going to do that. Instead, we're going to draw another resonance structure. So what we're going to do is, since this is allylic with respect to 4 and 5, or with respect to 4, what we're going to do is we're going to take this pi bond here, move it to the space between 3 and 4. And that will now give us another resonance form. That will give us another resonance form where there's a double bond between 1 and 2, and there should be a double bond between 3 and 4. So 3 and 4, there's another double bond. Okay, we'll get this structure, and when you calculate formal charge, 5 should have a positive charge on it. So we have 1, 2, 3, 4, and 5. Okay, so that's the new resonance form. So if you notice, what we've done in these or through these resonance forms is we've actually moved that positive charge from carbon number 1 to carbon number 3 and to carbon number 5. So we could actually spread it out. So going back to the introductory video on resonance, realize that the purpose of resonance is resonance actually makes molecules or species, they're more stable because it delocalizes the electron. So there is a positive charge that has been spread out. Okay, so it is delocalized, so that makes the species more stable. So these are all resonance forms of each other. So we can now go ahead and include the arrows, the resonance arrows here, and enclose them within square brackets. And what we've got is we've got 3 resonance forms for this structure that we started with. Okay, so those would be 3 resonance forms. So this was an example where we had a positive charge at an allelic position. Let's look at this next example here. We have a positive charge. Is it allelic? If you look at that carbon where the positive charge is, it is connected to a carbon which is part of a double bond, or which is vinylic. So that means yes, it's allelic. Is this positive charge allelic with respect to this double bond? It is not, because the positive charge is connected to this carbon, which is not vinylic. So then it is not allelic with respect to this double bond, but it is allelic with respect to the other double bond. So in a scenario like this, what we do is when you have a positive charge that's allelic, that's in an allelic position, we can take that pi bond and move it to the space between the vinylic carbon and the allelic carbon. And this would give us a new resonance form where this double bond, it's going to stay, doesn't go anywhere. Okay, and we have this 6-membered ring. So I've drawn a hexagon, and now there should be a double bond on this other end. And outside of it, there was a double bond earlier, but now there should be a single bond. Okay, so that's the resonance form that we're going to get. And then when you look at formal charges, this positive charge now migrates to there. Okay, well, the positive charge does not migrate. It's the electrons that delocalize, and as a result, the positive charge, the formal charge, should now end up on that other carbon atom. Okay, so we've got a resonance form. Now, this positive charge is also allelic because it is connected to the vinylic carbon, but what you would do is if you push these electrons over, you're going to come back to this resonance form. So you can go back and forth between resonance forms. But in this particular case, these are the only 2 resonance forms that I can draw which actually engage that positive charge or help spread it out, delocalize it. Okay, those are the only 2 that I can draw. So those are the 2 resonance forms in this particular case. Okay, so that's scenario number 3, where you have a positive charge at an allelic position. Now the positive charge can be on carbon, it could be on another element, doesn't matter. But what you're looking for is a positive charge that's on an allelic position. And then you can use the pi bond to do some resonance. Okay, let's go to scenario 4 here. Scenario 4. Scenario 4 is when we have a lone pair at an allelic position. Okay, we have a lone pair at an allelic position. Now this lone pair could be a negative charge, okay, because the negative charge basically implies 2 electrons, which can be considered as a lone pair. So this could be a negative charge. Okay, so you have a lone pair of electrons at an allelic positions, and we're going to look at a few examples to demonstrate this. So let's start with something simple. You have a negative charge over there. A negative charge there. And there. I think these are the examples that we'll use to basically convey this message. Okay. So now if you look at it, these are negative charges, but if you do formal charge calculations, what this negative charge means is that there is a lone pair here. And this oxygen here has a negative charge on it. It only has 1 bond to it. So based on the bonding that oxygen engages in, what this means is this oxygen has 3 lone pairs to it. That's why it has that negative charge to it. Okay, so now if you notice, we have a lone pair that is at an allelic position because this carbon is connected to the vinylic carbon. Lone pair at an allelic position because this oxygen is connected to a vinylic carbon. Lone pair at an allelic position because the nitrogen is connected to that carbon, which is part of the double bond. Okay, so these are all lone pairs at allelic positions. So when you have a scenario like this, when you have a lone pair at an allelic position, you can do resonance by starting at this lone pair. Okay, you start at the lone pair. So if I take, and in fact, before we go into this, I want to talk about Octet Rule a little bit more, because one thing that we have to do when we are drawing or when we are constructing resonance forms is we should never exceed the octet for the second row elements, okay? So let's calculate if the octet is satisfied for this carbon atom, that carbon atom, and that carbon atom. So if you look at this carbon, okay, bond line structure, this is a bond line structure. This has 2 hydrogens to it, so 2 bonds. So the 2 bonds are going to give us 4 electrons plus 2 bonds here, so 8 electrons. This carbon here has 1, 2, 3 bonds. There's nothing else shown on it. There's no charge. What means that, and that means there should be a hydrogen here. So it has 8 electrons also. Similarly, this carbon here has 1 bond here, a lone pair, so 2 plus 2, 4, and then it should have 2 hydrogens connected to it. So those 2 bonds contribute 4 electrons, so total of 8 electrons, okay? So the octet is complete, and each element has a complete octet at this point, okay? So what we're going to do is we're going to start with the lone pair at the allelic position. We take this lone pair and move it to the space here. And since these are all carbon atoms, it might be helpful to actually number these so that we can see. So we took the lone pair and we moved it to the space between carbon atoms 1 and 2. Okay, now think about carbon 2. Carbon 2 has a complete octet even before these electrons move. So if I just move that electron pair and I put a double bond here, that would install, or that would put 10 electrons around carbon number 2, which is more than the octet. Okay, so for that reason, to avoid breaking the octet rule, what happens is as and when this lone pair moves in, we have to move out this other pi bond, okay, to carbon 3. So basically push that out, so that we get to a scenario where we have now a double bond between carbons 1 and 2, single bond between carbons 2 and 3, and carbon number 3 has a lone pair, which means it has a negative charge to it. So we have 1, 2, and 3. Now, it might be helpful to actually draw out the hydrogen, so I'm going to do that here. Okay, so this is 2, this is 2. So 2 has 1 hydrogen on it, 3 has 2 hydrogens on it, 1 has 2 hydrogens on it. That's the scenario before we start. So now you can notice if we just take these 2 electrons and just leave them here, then carbon 2 is going to have 10 electrons on it. So that's what we're trying to avoid here. So now 1 has 2 electrons here, 2 hydrogens, 2 has 1 hydrogen, and 3 still has 2 hydrogens. And what you notice is in this scenario, the octet is still preserved. Okay, the octet is preserved for each of the second row elements. So these are 2 resonance forms of each other where we basically spread out the electron density. So resonance arrow, within square brackets, we've got resonance forms. Next example, we have a lone pair that is at an allelic position. So we can take one of the lone pairs, move it to the space between the carbon and the oxygen atom, and this basically brings us to a similar scenario. So what we're going to do is move that pi bond out, okay? And the result of that is going to be a double bond between oxygen and that carbon, single bond between the 2 carbon atoms, and a lone pair on that carbon. Oxygen used one of its lone pairs. It should be left with 2 lone pairs. No negative charge on the oxygen, but this carbon here should now have a negative charge, okay? And again, it's all based on Octet Rule, the formal charge that's been assigned, okay? So resonance forms, include them within square brackets. Third example, the lone pair on the nitrogen is also at an allelic position. So we can take the lone pair, move it to the space between nitrogen and carbon. At the same time, okay, this oxygen has 2 lone pairs already. At the same time, we take the pi bond, move it to the other end of that vinylic system, okay, the 2 atoms that are double bonded to each other. And that should give us a nitrogen that is now double bonded to that carbon atom. Single bond between carbon and oxygen. The oxygen should have 3 lone pairs to it, which would mean a negative charge. And similarly, the nitrogen used its lone pair. It has 4 bonds to it now. So that means this nitrogen has a positive charge to it. Okay. Again, I would encourage you to do the formal charge calculations if it does not make sense. Okay. That would be helpful. But as you practice more and more, I think the goal here is to actually make some of these connections that, oh, when nitrogen has 4 bonds to it, doesn't matter whether it's 4 single bonds or 2 single bonds and a double bond, doesn't matter. If nitrogen has 4 bonds to it, it should have a positive charge to it. Okay, so those are resonance forms. We include them within square brackets. Okay, so that's scenario number 4, when you have a lone pair at an allelic position. Okay, so I'm going to, and there's another scenario that we're going to discuss in a subsequent video. Bye.